Good morning, students. So today let us discuss the transformation from center of mass to laboratory frame. So there are two frames. One is center of mass frame, another one is laboratory frame. So there are two frames. But the experimental observation will be taken only in the laboratory frame. So laboratory frame in which we have experimental side will work out. Theoretically, we will use only the center of mass frame. But when you are talking about these two frames to observe any scattering experiment, and this will be explained by theoretical model. That is, in the center of mass frame, the theoretical calculation will be very simple. In the center of mass frame, in which we have a two-body system. Of course, scattering experiment is a two-body system. And we have 6 coordinates to denote this one. So we will have to have 2 particles. So each particle will have 3 coordinates. So we will be using 6 coordinates, correct? So out of 6 coordinates, to simplify the model, we will be using 3 coordinates through mu, through reduced mass. So we learnt already using Schrödinger time independent wave equation, we have replaced m by mu. So the two body problem will be converted into single body problem, in which we are going to use only 3 coordinates. So this is simpler one. Theoretically this can be explained, and this can be explained only by means of center of mass frame. So that is like that. Whereas in the laboratory frame it is entirely different. So all the experimental observation will be taken only in the laboratory frame. Both the results should be equal. So in the laboratory frame, we have 2 particles. So we are going to consider 2 particles. One is the incident particle, another one will be a target. The target is fixed. Target is constant, fixed. It is fixed in the laboratory frame. Whereas in the center of mass frame, the center of mass is fixed. The coordinates move relative to each other with a velocity which is equal to the velocity of center of mass in the observed laboratory frame. So we are going to have 2 frames today, in which the experimental will be taken into consideration in the laboratory frame, whereas the theoretical side will be taken in the center of mass frame, and there will be a connection between these two. And we are going to observe how we are going to transform from one frame to another frame. So what is the connection between these two? So we are going to look into. Now we are going to consider 2 particles, m1 and m2. So we are going to consider 2 particles, m1 and m2, and in the laboratory frame, L stands for laboratory frame. Okay? In the laboratory frame, this is moving, this is fixed. In the laboratory frame, the target is fixed, the scattering center is fixed, whereas this is moving. So m1 is moving with velocity v1L, whereas m2 is at rest in the lab frame. Now velocity of the particle of mass m1 is nothing but v1L. The velocity of m2 particle is nothing but v2L, because as we said, this is fixed, so v2L equal to 0. So this is before collision. Now this one will collide with a scattering center. Okay, so what will happen in the laboratory frame, that we are going to observe. So after the collision, the incident particle will suffer an angle theta 1L, and the target material will suffer an angle theta 2L. Okay, so theta 1L is here and theta 2L is here, and of course this will have a velocity v dash n1. See, v1L, this is v2L, this is v dash 1L. Okay, after the collision, the incident particle will have this velocity v dash 1L, and this velocity is nothing but v dash 2L. Okay, now we are going to have these components, xy components. This is x and this is y direction, and x component is nothing but v dash 1L cos 1L. Is it okay? If it is theta 1L, the velocity according to the velocity is v dash 1L. The x component is given by v dash 1L cos theta 1L, and this is your vertical component. Okay, this is y direction. So v dash 1L sin theta 1L, and this is for the incident particle. This is for the target material. Similarly, this can be resolved into two components. One component is nothing but V dash 2L cos 2L. The other component is nothing but V dash 2L sin theta 2L. Is it okay? So this is after collision, this is before collision in the lab frame. So in the lab frame, we are going to keep this target material is at rest. So this is what laboratory frame is described. Whereas in the center of center of mass is fixed, as I said earlier. In the laboratory frame, the target material is fixed, whereas in the center of frame, the center of mass is fixed. The observer is somewhere here. The observer will observe both the things, both the particles. They will collide with each other. The observer will observe that these particles together will move about its center of mass. Okay, now this is before collision, and after collision, what will happen? The observer here, he observes both the particles. See, both the particles, they will collide with each other. This particle will move this way, whereas this particle will move towards him. So this is what the observer will observe. This will move towards him. So that's why we written like this. See, observer is somewhere here, and this is your incident particle. This is your target material, and this incident particle moves somewhere away from him, whereas the observer will observe this target material that moves towards him. Okay, so here this is what we said about 6 coordinates. We are going to convert these 6 coordinates into 3 coordinates. Of course, we know that scattering problem is a 2-body problem. We know already. And center of mass is fixed. Now this is before collision in center of mass frame. This is after collision. And just look at the angle between this one and this one is nothing but your theta c. Okay, c stands for center of mass, and the final velocity is v dash 1c. Here it is v1c. The mass of the first particle is v1c. Mass of the second particle, since the target material, is v2c. So this is your v dash 1c, and this must be your v dash 2c. Okay, you can also resolve into two components, v dash 1c cos theta c, and this is your v dash 1c sin theta c. Okay, and of course theta c is here, so this must be your pi minus theta c. Now our aim is to find out the relation between lab frame, the angles of lab frame and center of mass frame. So this is our idea. That's the relation between the transformation from center of mass to laboratory frame. So we are going to find out the relation between theta 1L and theta c. Theta 1L is nothing but this one, theta 1L in the lab frame. Theta 1c is nothing but in the center of mass frame. So we are going to find out the relation between theta 1L and theta c. Similarly, we can also find out the relation between theta 2c, theta dash 2L and theta c. So we can also find out. Okay. So this is the coordinate system which connects in the center of mass frame, which is given as like this. So we have m1, m2, so two particles, they will collide with each other, and the coordinate of this one is about its origin is nothing but r1c, and coordinate of this one will be r1l. This is your center of mass, and this coordinate of this one will be from center of mass to origin will be your capital R. So relating all the three, that will have the equation this one. So your r1l, which is equal to r1c plus capital R. Okay, so r capital R denotes the position of the center of mass with respect to, so your center of mass with respect to the lab frame. Okay, so your r1l equal to r1c plus r. Just to differentiate with respect to time. So rate of change of r1l will give you velocity v1l. Just to differentiate. Okay, so r1c will give you, rate of change of r1c will give you v1c. Rate of change of r will give you dr by dt will give you v center of mass, where vnl and v1c are the velocities of mass m1 in the lab frame and center of mass frame. So before collision, vcm is the velocity of center of mass with respect to the lab frame. Okay, similarly velocity after the collision. So velocity of m1 after the collision. This is before the collision. This is after the collision. You just go with dash prime. So v dash 1l which is equal to v dash 1c plus vcm. Vcm is fixed. Vcm is constant. So similarly, we can also resolve into components. We can write the equation into components exactly like this. So how it is written here? See, just look at the picture. So v dash 1l cos theta 1l. Okay, this is in the x direction. Similarly, here also v dash 1c cos theta c is in the x direction. So we can write v1l cos theta 1l, which is equal to v dash 1c cos theta c plus vcm. And this one v1l sin theta nl is in the y direction, and v1 dash 1c sin theta c in the y direction. So this can be written as exactly equation 6.149. So v dash 1l sin theta 1l which is equal to v dash 1c sin theta c. So divide this by this. So this by this will give you this equation 6.150. Okay, you divide this equation by this equation, that will give you, so v dash 1l will get cancelled. You have sin theta by cos theta will give you tan theta 1l, which is equal to this divided by this will give you this. Okay, now I am going to divide both denominator and numerator by v dash 1c. So v dash 1c will get cancelled, v dash 1c also will get cancelled. You have vcm divided by v dash 1c. So now look at this left hand side. This is theta 1l. Look at the right hand side. It is theta c. So there is a relation between theta 1l and theta c. This is a relation. So this is the transformation from lab frame into center of mass frame. So this is a relation. Provided we will have to find out vcm divided by v dash 1c. That's all. So if you are trying to find out vcm divided by v dash 1c and substitute here, and there will be a relation between these two. So that's the idea. Okay. Now for that, what we are going to do is we are going to consider this the collision is elastic collision. So we are going to apply two things. One is about momentum, another one is kinetic energy. Momentum is conserved and kinetic energy is conserved. So we are going to assume these two for the elastic collision. If it is so, then momentum is conserved. Then we can use before collision. We can use this equation. Momentum P equals mb. So m1 v1l plus m2 v2l, which is equal to center of mass. Okay. So vcm multiplied by m1 plus m2. And of course, your v2l equal to 0 in the lab frame. We know that the target material is at rest. So we have already considered. So this will go off. So you have vcm which is equal to m1 v1l divided by m1 plus m2. We just substitute this equation in 6.146, which is given by this equation. So already we looked into this equation, v1l equal to v1c plus vcm. You just substitute this one here. So substituting, we have v1l which is equal to v1c plus, instead of vcm you just substitute m1 v1l divided by m1 plus m2. You bring this term to this side. So we have v1c which is equal to v1l minus this term minus m1 v1l by divided by m1 plus m2. So you just pull v1l common out. So that will give you 1 minus m1 divided by m1 plus m2. Take the LCM. So that will give you m1 plus m2 minus m1 divided by m1 plus m2. This m1 will cancel. You have m2 divided by m1 plus m2 multiplied by v1l, which is nothing but your v1c. Okay, so we are going to use this expression later. Now the total momentum before collision is equal to after collision in the center of mass frame. We know already for the elastic collision. So momentum is conserved. So before collision, this is your equation, m1 v1c equal to m2 v2c. So where v2c is nothing but m1 by m2 v1c. So this is after collision. So m1 v1 dash 1c. So we have resolved into components. V dash 1c cos theta c, which is equal to m2 v dash 2c cos theta c. And cos theta c will get cancelled. You have v dash 2c which is equal to m1 by m2 v1c. We are going to use all the expressions here, okay, in the kinetic energy expression. As I said earlier, for elastic collision, momentum is conserved as well as kinetic energy also is conserved. Okay, so using kinetic energy equation. So kinetic energy of the particle is the same before and after collision. The kinetic energy is conserved, so you are going to use this equation. Okay, so before collision and after collision. So half m1 b squared 1c plus half m2 b squared 2c, which is equal to, this is after collision. So before collision is equal to after collision. Okay, now we are going to use the expressions as I said. V2c is given by this expression and V dash 2c is given by this expression. You just substitute here. So just a substitute. So we have the first term like this. Second term is substituted by this expression m1 by m2 b dash 2c whole square. Okay. So plus, which is equal to 1 by 2 m1 b dash squared 1c plus 1 by 2 m2. You just substitute. Substitute for v dash 2 square. Okay. Whole square. So we will have this expression. Now this first term is, let it be like this. You have m1 square and you have m2 square is there. One m2 will get cancelled. You have m1 square divided by m2 as it is. The next term will be as it is like this. Similarly, this term will let it be like this. And here also we have m1 square divided by m2 square and one m2 will cancel. You have this term. And look at the expression 6.160. 160. So this is before collision, and this is after collision. This must be equal to this and this must be equal to this. If it is so, this must be equal means V1c equals V dash 1c. V2c is equal to V dash 2c. It implies that the velocity before and after collision are equal in elastic collision. So it implies that the speed is equal, the velocity is equal before, or otherwise you can say the velocity is exchanged in the elastic collision. Okay, before collision and after collision the speed is equal, the velocity is equal. Here also velocity is equal. So very important relation which we are going to use. Okay, now we have already these expressions earlier. These two expressions already we discussed. VCM is given by this expression, V1c is given by this expression. You divide this by this. So divide this by this. Will give you m1 v1l divided by m1 plus m2 divided by m2 divided by m1 plus m2 v1l. And this one and this one will get cancelled. Correct? We have m1 by m2, m1 by m2. And v1l also will get cancelled. So we have vcm divided by v1c, which is equal to m1 by m2. But already we know that v1c is nothing but v dash 1c. So we are going to replace, instead of v1c we are going to replace with v dash 1c. Okay. So your vcm divided by v dash 1c equals m1 by m2. So this is what we need. vcm divided by v dash 1c, which is nothing but your m1 by m2. So that's all we have calculated now. So we know that tan theta 1l, which is equal to sin theta c divided by cos theta c plus vcm divided by v dash 1c. So we have replaced with m1 by m2. Is it okay? Now we know the expression tan square theta l, which is equal to secant square theta 1l minus 1. We know already. Okay, this relation we know. Tan square theta equal to secant square theta minus 1. So we know already. So just to bring this 1 to this side, we have tan square theta plus 1, which is equal to 1 divided by cos square theta l. Okay, so cos theta can be written as 1 divided by root of 1 plus tan square theta 1. You substitute for theta squared here. The expression for your theta, tan theta 1l, which is given by this expression. So 1 plus sin theta c divided by cos theta c plus m1 by m2. Just to square the term and take the LCM. When you are going to square the term, that will give you sin square theta by c. Square the term, cos theta c plus m1 by m2 whole square. Take the LCM, will give you this expression plus this expression divided by this one. Okay, is it okay? Now bring this term denominator to the numerator. So that will give you, because it is under root, so that will give you cos theta c plus m1 by m2. This term you just expand. So you have a plus b whole square formula. So cos square theta will give you this first term, and this will be your 2 m1 by m2, 2ab, and this one will be b square. So m1 square divided by m2 square. You add these two will give you answer of 1. So you have 1. Remaining term we have written. Now look at the left hand side. This is theta 1L. Look at the right hand side. It depends on theta c. So this is a relation between lab frame and center of mass frame. Okay, so this is the relation which we want to get. Okay, the transformation from lab frame into center of mass frame is given by this expression 6.166. So this is the relationship between the scattered angles theta 1L and theta c of the incident particle. This is for the incident particle in the lab frame and the center of mass frame after the collision. Similarly, we can also get the same relationship for theta 2L and theta c. Okay, so can you remember? So we have obtained this is theta 1L. So we can also get the same relation for theta 2L and theta c. We obtain the relationship between theta 1L and theta c. We can also get the expression for theta 2L and theta c. Okay, theta 2L and theta c for the of the target materials. So this is for the incident material and this is for the target materials in the lab frame and the center of mass frame. Thus we can transform from center of mass to laboratory frame. So we can transform from one frame to another frame. Okay, that is the end. So in this class we have discussed two frames. One is a lab frame, another one is center of mass frame, and there is a relation between these two, and we can also transform from one frame to another frame. So thank you students. We will see in the next class.